Hello and welcome to Good Drugs. I'm Michael Fiedler, PhD, and I'm of the belief that in order to get through this thing called life, we need potions, elixirs, magic pills, and it's just a matter of finding good ones. But today, we're not going to talk about a good drug, we're going to talk about a dead drug. And that dead drug is called Opicinumab. And like all the drugs on this podcast, this one is near and dear to my heart. I had the opportunity to work on it for a while, and it's a really cool drug. It was championed by a company called Biogen, and it's a was an interesting attempt to treat multiple sclerosis in a different way than a lot of other treatment options out there. And it wouldn't necessarily replace those options; it would just be an add-on. So let's first talk about a little bit about MS. So essentially, what happens in MS is that you have an overactive immune system that chews on myelin, which is the protective coating of your neurons. So if you think of your neurons like a wire, myelin is the rubber coating that surrounds it. And your immune system attacks it like piranhas attacking something in the water and strips off this myelin, exposing your neurons, and then they kind of wither and die. And that's how you get disability in MS. And so essentially all MS treatments that are approved attack the immune system somehow. They'll either kill immune cells, like what Ocrevus and Mavenclad do. They can sequester immune cells in certain parts of the body, like what Gilenya does. They can restrict cells from crossing the blood-brain barrier, which is what Tisabri does. So they all hit the immune system one way or another, or at least try to. And Opicinumab was coming at this from a different perspective. And the perspective that it was coming at was trying not to suppress the immune system from harming the nervous system, which is what all the other drugs do, but rather to activate or promote the body's ability to repair that attack. So its main target was not to suppress inflammation, which is what a lot of the other drugs do, but to promote myelination or re-myelination in the event of an attack. And the science behind it is decent. I wouldn't call it A plus, but I also wouldn't call it C plus either. It's solid, but it is fraught with sort of human elements that I'll get into. But Opicinumab, the name comes from a oligodendrocyte, which is a mouthful, precursor cells. That's where the OPC comes from, a oligodendrocyte precursor cell. And then the MAB is a monoclonal antibody. So what this Opicinumab binds to is a protein called LINGO-1. And LINGO-1 has sort of an interesting role in the human body in the sense that normally it suppresses myelin formation. So if you think about a growing person, like an embryo, a fetus that grows into it's an infant and then a toddler and then a teenager and then an adult, you have like nervous system development. And in the early portions of your life, LINGO-1 is not active, and your brain sort of forms and you develop your nervous system. And then as you get older, maybe 10 years old, this LINGO-1 protein becomes activated and it starts suppressing your body's ability to grow myelin. And the way it does that is it suppresses the formation of these things called oligodendrocytes. And oligodendrocytes are cells in the brain that add and provide myelin and coat your nervous system with myelin. So imagine them like if you're thinking about an airplane at an airport that has to have its like wings de-iced, or it has to have sort of its edges buffed. Think of those like think of the sort of the guys out there with a hose as oligodendrocytes who are modifying your nervous system. Oligodendrocytes themselves are not nerves, but they reinforce nerves by adding and coating them with myelin. But your body thinks that once you reach a certain age, your nervous system is essentially developed, so your body starts pumping out this protein called LINGO-1, which suppresses the formation of myelin. And so what Opicinumab attempted to do was to bind to this LINGO-1 and occupy it so that your body could restore its ability to make oligodendrocytes to then increase its restorative remyelination capacity. And starting in the sort of the preclinical data sets of like just tissue culture and then into mice and then moving into humans, the data looked somewhat promising. The challenge, though, is once you start stepping out of the scientific realm and into the clinical one, you have to begin to make choices that can really make it difficult to harness science. And what I mean by that is it's easy in a tissue culture system to say, a cell is doing more of something or it's doing less of something because you can look at it through a clear microscope and you can kind of see it. There's all kinds of stains that you can do. If you're not talking about a person, it's not as easy. And so measuring myelin and myelin formation has been a really challenging ask for the medical community. There are lots of sophisticated metrics that can be used to do it. Things like diffusion tensor imaging or PET positron emission tomography. There's a lot of different markers that can be used to measure myelin, but they're not perfect. And even if they were perfect, myelin itself is the intermediate between sort of a healthy and an unhealthy neuron. So if you lose myelin, your neurons are exposed, but it isn't as simple as you lose myelin, you get clinical symptoms. So the reason why I spell all of this out is that should you be giving somebody the capacity to remyelinate, it would be hard to tell if the drug was actually working. As I said, it's easy in a tissue culture system, or it's easy with a mouse if you can injure it and then sort of see how the body repairs itself. But with a human being, it's not as simple. And that nuance is just one of the initial complexities about this drug. And so one of the reasons why it died is that it didn't hit its endpoint in a phase 2 trial called Affinity. What's interesting is that it didn't hit its endpoint in a previous trial called Synergy either. But Biogen didn't give up, and they wanted to try to find ways to isolate a more specific patient population that they thought could work, or refine the dose with which they were giving it to just get it right. But it ultimately didn't work. And if you think about the endpoint, for example, it was a combination endpoint. It had things like disability, it had things like upper arm function, it had things like time 25-foot walk, all kind of rolled up into a singular endpoint, because the body's conceivably how a patient responds to something like this would be difficult to measure, and you're not really sure how it's going to present, because symptoms of MS are very nebulous. It can be everything from tingling in your hand to blurred vision. It's the way that these symptoms manifest is really diverse because your neurons are very diverse, and it's just a matter of which ones are getting fried. So they had this cluster endpoint approach, and if one of those endpoints doesn't hit, then they all don't hit. And they all have to hit for it to hit, for example. So with a very subtle effect on the disease itself, it's not surprising that the combined endpoint didn't work, because it was just throwing too much ish against the wall and then just not enough of it sticking, essentially. The other thing that was a challenge in the initial trials is how to dose this drug. So when they first tried it, they did it following a relapse. So you have a relapse, and ideally you get this drug within 4 weeks to try to restore the myelination capacity. So if somebody were to experience a robust symptom of MS, they get hospitalized because they have as I said, tingling in your hands or some form of clinical symptoms. Give them the Opicinumab, and then ideally their body will be able to recover from that attack and potentially remyelinate. But that's assuming a lot. That's assuming that you can actually get the patient to the drug quickly, which may not be the case, that the drug's going to work in that narrow time frame, which is also not a given. So it wasn't surprising that this initial trial didn't work, because just getting the drug to the right patient at the right time to fix the damage that was done, it was too cumbersome, and it didn't flesh out. Another thing that was tried, and I believe in the Renew study for Opicinumab, which was another phase 2, was looking at patients with what is called optic neuritis. And optic neuritis is one of the first precursor steps to MS. Basically, you have demyelination of one of your optical nerves. So it's something that causes distorted vision in one eye, not both. That's how they know it's optic neuritis. And that is oftentimes the first sign of MS, because if you get another clinical symptom like tingling in your hand or numbness in your foot or something, that would be a second symptom, and then somebody could define your disease as MS. Whereas if you just have optic neuritis, they'd be like, well, you have optic neuritis. If you would have to get optic neuritis again or another symptom similar to optic neuritis to think that you have MS, or what they call relapsing MS, relapsing remitting MS. So it kind of comes and goes. So they tried it in patients with optic neuritis, and there was some modicum of efficacy because you're getting it at the first signs of MS. So ideally, you're fixing the initial demyelinating events rather than waiting for someone who's already too far gone to remyelinate them. But findings were a bit blurry, no pun intended. But there was this expectation that inhibiting LINGO-1 could still work, and in theory, the science was decent. But there are also things associated with the antibody itself, or what specifically it targets, because Opicinumab interacts with membrane proteins, but if you have the wrong antibody, it may interact with cytosol proteins, so proteins within the cytoplasm of a cell and not the membrane proteins. So exactly what the protein is binding to really matters. In talking about Opicinumab to someone who sort of looked at it very closely from an investor perspective, one of the things that this person told me was that a lot of the work came out of one lab, and there was, which was somebody at Biogen, but all of the data, or at least the bulk of it, came from a small cluster of individuals, rather than like a diverse group. But because if you look at the diverse totality of Opicinumab and LINGO-1, the data aren't as sterling, which is why the data is decent but not great, which also makes sense. So you have a target that's really interesting. This LINGO-1 is a really interesting target, and if it could be inhibited, then it's possible that you could have activation of oligodendrocytes or differentiation of oligodendrocytes to then remyelinate. But how you hit LINGO-1 is the challenge. How you measure what the output of LINGO-1 is the challenge. So the target of LINGO-1 is still probably legit, but our ability to hit it well enough and to measure the effects of it well enough is not that good. And so Biogen, the Opicinumab had a very slow death. Its first failed trials kind of hit in like 2015-16, and they're like, oh, we're going to reanalyze our data and we're going to try again. And now in 2020, and actually just at the end of last month, they formally said that they're discontinuing Opicinumab. So, it was sort of expected that, or at least the expectations of Opicinumab have slowly wilted over the last 4 or 5 years, and now it's just official that the drug is dead. But it's unfortunate because the idea of remyelinating the nervous system would be a definitely improvement in the way that MS is treated. So rather than just suppressing the immune system in a different way, which is what a lot of new drugs are going to do, actually stimulating remyelination and recovery would be a real game changer. But as this failed drug indicates, is that it's really hard to measure myelin clinically to even get it through approval. And sort of the last thought that I wanted to kind of leave you with and to kind of end this is that we're in the backdrop of this crazy pandemic and COVID and such. And it occurred to me that what if, rather than going after this with a monoclonal antibody that may or may not function exactly the way that we want to, what if there was a vaccine for it? And what if, because LINGO-1 is really only used, or at least only comes on later in life, if somebody's over the age of 20, or maybe somebody already is diagnosed with MS, you just give them this LINGO-1 vaccine, and now anytime LINGO-1 shows up, it is inhibited, and the body's ability to generate oligodendrocytes is perpetually activated, and it would be a cheap way of ensuring oligodendrocyte activity in the body. Now, that's just me tossing out a very random idea, but it's something that could conceivably salvage what's otherwise been a really long journey in terms of a component of multiple sclerosis that otherwise would be abandoned, And it's something that any MS patient would want. They would want to have their myelin restored because that's what's driving their disability. And I couldn't help but connect the dots given the fact that we're sort of immersed in this vaccine conversation with COVID. But anyway, I thought Opicinumab its death is, I'm not surprised that it happened, but I wanted to kind of draw attention to it because it's really another one of these really interesting stories about medicine, and one that kind of breaks my heart, even though I was pretty sure it was going to die anyway. But that's Opicinumab. And if you're interested in more good drugs or dead drugs, feel free to subscribe to my channel.